All right. Holler and wave from the back if I can't be heard. So I'm very excited to be here today to tell you about the quantum simulator work that we are building up in my lab. So why don't we get started? So I want to start by introducing the hardware platform. That is a really awkwardly steep angle. Okay, I'm going to stop looking at my slides. Yeah, I usually like to point, but I'm going to have troubles. But okay. So the hardware platform that we work with is superconducting qubits. And so that means that we have two main sort of building blocks from which we can build up a simulator. So the first half of our toolbox are microwave resonators. And the kind that we like to use mostly in my lab are coplanar waveguides. And so there's a circuit model cartoon in the upper right of what this looks like. And so you should think of this as a two-dimensional version of a coaxial cable, that there's a central conductor and ground planes surrounding it. And this forms a very nice guided mode for RF or microwaves, as long as that center pin is continuous. But if you cut a hole in the center pin, then you break the coaxial geometry and you cause a very strong reflection. And so this here is a 1D cavity for microwave photons, where they're guided along the end until they hit the gap where there's a change in the capacitance and inductance, and then they bounce back. And so this is our favorite microwave cavity. This is the sort of cartoon picture for the lithography. In practice, this is more what they look like, because these are very large structures for microfabrication, around 7 or 8 millimeters long. And so we typically fabricate them with these extra meanders in here to compactify the structure. And the fact that we can do that and add these extra meanders to change the shape or the packing density is actually going to be really key to some of the lattices that we can realize in this geometry. And if you don't like looking at CAD, it's a harmonic oscillator with conjugate degrees of freedom, charge, and flux. And so this is half of our toolkit. We like them a lot because they're easy to fabricate and we can control them very well, but they're perfectly harmonic and linear, so we need some other ingredient. And the other half of the toolkit is, of course, superconducting qubits. The only one that I'm going to talk about today is the transmon qubit. And so this is a circuit model for this one. It's a capacitor in parallel with a Josephson junction, indicated by this X. This particular version has a squid loop here, meaning that it's a flux-tunable Josephson junction. And so the way that you can think about this is as an anharmonic oscillator. So instead of charge squared flux squared, it's charge squared cosine phi. And the additional harmonic terms in the cosine are going to make the level spacing unequal. And in fact, the transmon regime is actually where this EJ coefficient is by far the largest. And so you can get a lot of intuition for this system, thinking of it as a particle in a cosinusoidal well. And so the fact that the well softens up at the top causes the level spacing to be unequal. And so the lowest two bound states in this well are the 2 qubit states of the transmon. And if you don't whack it too hard or too fast, it stays down there. And so this is our 2-level system that we can combine with the microwave resonators that I introduced on the previous slide. And what's really nice about this is that you can simply take one of these transmons and fabricate it inside a coplanar waveguide very easily. And so this is a rendering of the CAD for a device that I will show later on. So the yellow and blue here are actually the capacitor in the transmon. This red area here is where the squid loop is. And this is the center pin of the coplanar waveguide, which is housing that qubit. And so they're very easy at the lithography level to just plonk together. No tweezers needed. They don't fly away. You fabricate it. It stays there for good or ill, whether it was a good qubit or not. And the other very nice thing about this platform is that it natively realizes this Jaynes-Cummings style interaction. And so that means that we have a harmonic oscillator for the cavity, a 2-level system for the qubit, and the native interaction is this intuitive energy exchange where you can swap a photon for a qubit excitation back and forth. And this is the standard, basically minimal model for light-matter interaction. And what's unique in the circuit QED system is really the energy scales. So we're talking about gigahertz level qubits and gigahertz level resonators, but coupling strength of order 100 megahertz or more. And so these are very, very naturally strong coupling systems where you have a lot of control over a very powerful light-matter interaction. And this is the standard set of building blocks for all superconducting circuit devices. And people tend to view this Hamiltonian in one of two ways. There's a more traditional quantum computing approach, which is to say we're interested in the two-level system. We want the spin, in which case what the resonator is doing is controlling the coupling between the spin and the environment and giving you a very well-directed input and output channel to get control signals in and out. And in that sort of framework, you naturally end up thinking about photon-mediated or photon-controlled spin models. Or you can turn this around and think about it the other way and say, actually, no, I prefer harmonic oscillators to two-level systems, in which case the qubit is coming along and endowing your formerly harmonic oscillator with a nonlinearity. And so you can think about using the qubit to control photon-photon interactions, or you can think about using the photons to control qubit-qubit interactions. Both of these things are possible. And so what we like to do in my lab is to say, this isn't enough degrees of freedom. And so we like to think about what happens when you go to a multi-mode case where there's more than one photon mode in play. And what are the new things that you can do? In particular, what kind of interesting simulations you can do. And this is our kind of idea of where we should go in multi-mode. So this is a lattice. It was fabricated in the Hauck lab a little bit over 10 years ago now. And so each one of these squiggly lines here is now one of these coplanar waveguide resonators. And they're coupled at these teeny tiny little black dots. And if we zoom in, this is what the junction looks like, or this junction point. And so what's going on is you have the center pin between three different resonators are converging on the same point. There's a lot of extra capacitance there, and so a photon that's rattling around in this resonator can hop over onto one of the neighbors. And so we really like to think about this actually as a capacitively coupled tight binding solid for photons. It's very akin to a minimal model for non-interacting electrons hopping around on lattice sites. The on-site energy is set by the resonant frequency of the resonator, and the strength of the hopping comes from this capacitance region here at the end. One minor point is that the sign of the hopping is unusual. So I think we all learn in quantum mechanics class that the ground state of a system should have a slowly varying wave function. So things with long wavelength are at low energy, and things with rapid variations and rapid phase changes are at high energy, but actually this system is reversed. So the long wavelength things are at high energy, and the rapidly oscillating things are at low energy. So if any of you have seen the band structures that I put up before, they're going to be upside down from how they would usually appear. But this is more of a side note for this incidental minus sign. In addition to this minus sign, oops, sorry, wrong order of slides. So that was a purely resonator lattice, so that's just coupled harmonic oscillators. And so what we want to do is think about what happens when you put qubits into this lattice. What is the kind of phenomena that you get? And so this is data from the Shulkov group with a single qubit in a single cavity. And so what they're doing here is they've tuned the qubit to be resonant with the cavity, and they're doing spectroscopy of the excitations. And at low power, you get the vacuum-Rabi splitting. So this is showing you one hybridized light matter mode and another one. And what's really amazing about this data, if you come from AMO, is that as you go to higher power, you get these cleanly resolved lines, which are multiphoton transitions to the higher excited states. And so there's the one excitation, two excitation, three excitation states of the system are actually spectrally resolved. This interaction is so strong. This is a single mode, but this interaction is so enormous, and since then the lifetimes and the line widths have gone down, and so that you can get this kind of excitation number resolved behavior even in systems with larger, more delocalized modes. And so that's one sort of thing that you can look at. The other is to look, as I said, at the effects of the photons on the qubits. And so if you put two qubits in a cavity, sort of the natural interaction that you would get between them is a photon-mediated exchange. One qubit that's excited de-excites, emits a photon, and the other one absorbs it. So you have this sort of flip-flop style interaction. And if you have a single-mode cavity, if they're in the cavity, they talk to each other. And if they're not in the same cavity, then they don't. It's a very digital do they, don't they, which is nice and clean for a digital architecture, but in terms of making a spin model, that's a very, very limited short-range interaction. On the other hand, if you go to a multi-mode system where you have more than one photon mode in play, then you get that same sort of flip-flop interaction, but now summed over all of the different modes, because you could emit and reabsorb all of these different kinds of photons, and so that's what this sum here is. And so the interference between all of the different photons that you can emit causes you to develop spatial structure in this flip-flop interaction. So this is well known in conventional lattices with a quadratic band edge, where you get an exponentially localized bound state. So this has been measured at Princeton in the Hauck lab a few times, and by now in several other groups. But sort of the mission in my lab, especially in terms of our RQS goals, is to take these strong light matter interactions and these spatial photon-mediated qubit-qubit interactions and take them to new lattices that let us do different things from conventional ones. And so what are these new lattices that we can go to? Well, so the key really lies in two aspects of the hardware. And so the first is that our resonator is actually deformable. So this is the CAD for two different lattice sites. And so we're looking at this in the optical frequency domain, and you say, well, that's a totally different shape from that one. But for a microwave photon that's confined to the waveguide, they only care about how long the waveguide actually is. And so the frequency just depends on the length, and it doesn't care if you put one meander in or two. And the hopping very conveniently comes from what's going on at the end rather than what's going on at the middle. So you can change the shape in the middle without affecting the hopping. And so what that means is that you can basically choose within reason the form factor of your resonator and pack things in a non-uniform way, and you can try to make things fit that wouldn't otherwise have fit on a flat 2D chip. So we're not limited by the conventional rules of crystallography. So that's one aspect. The other aspect that's important is that our resonator is not a point-like object, it is a line-like object. And so if you look at photons hopping in this lattice, you need to look at a lattice like this that has a lattice site for every resonator and a hopping if the two resonators share an endpoint. And so even though this looks honeycomb-like, the actual description that we get for photons in this lattice is a Kagome-like lattice. And it turns out these have a name in mathematics. These are called line graphs. And there's books and books and books on them if you talk to the right person who knows how to find them. And this has deep implications for the band structure. That basically everything that I will show is going to be some form of generalized Kagome lattice. And they have an overwhelming tendency to produce flat bands. And so we have flexibility in how we pack the resonators in, and we have this very strong tendency to produce unconventional bands with very large degeneracies in the single particle physics. And so this is what lets us go to new places. It's particularly easy to see what this does for the photon-mediated qubit-qubit interactions. So one thing that we can do is we can make a lattice that would normally have to live on some curved surface. And so this is an example from when I was a postdoc here in the Hauck lab. And so this is a hyperbolic lattice. And so the photons hopping in this lattice are moving as if they were on a constantly negatively curved surface. We've shown that we can make this for the photons, and we have theory results showing that if you put qubits in this lattice, then the spin-spin interaction will inherit the hyperbolic metric from the photons. So you can go to hyperbolic graphs, which are normally very, very hard to access. And it turns out that the flat bands that we make, we know how to make them isolated, and they consist of highly oscillatory states which tend to produce something like a frustrated short-range magnet. And so these are sort of, broadly speaking, the two kinds of ingredients that we can get from unusual packing or these very large degeneracies of interesting states. And so that's what we set out to do in my lab, is to take these basically theory results that I've presented so far and this resonator-only device and actually go so far as to put qubits in here and see what happens. And so that's what I'm going to tell you about basically for the rest of my talk. Is the prototype device that we've made and characterized and developed measurement techniques for. And so our target is actually going to be this lattice. So the resonators are going to be laid out like this, and the hopping model is going to look like that. And the reason that we chose this is it's a quasi-1D lattice, so we can get a nice bulk with very little boundary without too many resonators. And it has basically all of the kinds of bands that you can get in one dimension. So it has a normal quadratic band, it has a linear band crossing, it has a gapped flat band, it has an ungapped flat band, it has sort of everything. And so this was the perfect device to make, to test out what does it look like, how do we measure this thing. That's the theory. Many months of labor later, that's the design. It's not easy to pack all this stuff in and make sure that it doesn't crash into itself. And so what we have is 9 unit cells wandering around this chip in an S curve. 1 unit cell here in the middle is highlighted in red, and so it's got 6 resonators, each repeated 9 times. And then we've put 3 flux tunable qubits into this device, which are shown in these highlighted patches. And so they have actually individual flux bias control lines, and so we have these 3 qubits that are at different inequivalent, some of them inequivalent sites within the unit cell that we can tune into and out of resonance with the photonic bands. For those of you with an eagle eye, you will notice the little purple caterpillars crawling all over this device. And so what those are actually copies of the qubit. So this is the main qubit. And what you can see is that you have to carve out a relatively large chunk of the ground plane to place the qubit inside. And so if we put the qubit just at a few isolated sites, it would actually detune those sites. And so what we do is we write the capacitor for the qubit everywhere, and the junction, this sort of red thing here, only in a few select sites. And this helps us keep the disorder levels down while having qubits at the sites that we choose. So this is what it looks like when it was made. So this was made about last February. So this is the device after photolithography. And so everything that you see in black here is a layer of tantalum superconductor. And then where you see white, you are looking through the 8-micron gaps in the center, in the coplanar waveguides, to a white tech wipe in the background. Once you package it all up, it's a lot harder to see everything. You mostly just see wire bonds. For those of you that have ever used a wire bonder, you know how many hours of labor that represents. And so we cooled it down, and this was one of the first preliminary measurements that we could do. And so let me walk you through a little bit how we measure these devices. And so we have an input port on this side and an output port on that side. And so the natural thing for us to do is look at transmission of microwaves. Try to send a microwave from one side to the other. If there's no mode, it shouldn't go through. If we're resonant with a lattice mode, then it should go across. And so that's what's shown in a cut down here. Each one of these peaks is the input microwave tone hitting a resonance in the lattice and going through. But since the qubits are flux tunable, we can apply a voltage to the flux bias line, and that creates this series of disturbances. And so what that is that one of the 3 qubits is passing through this lattice, leaving this trail of avoided crossings in its wake. And if we zoom in down at the bottom, you can see it a little more clearly. Transmons tune in a periodic fashion, and so this one's actually going through and back up again. And so what this data shows is that we have high Q resonant modes, qubits coupled to them strongly, and so that we are getting avoided crossings with the normal modes of the lattice. So we have basic functionality. And so what we've really spent the last year doing is trying to verify that we built the lattice that we set out to build, and that we can develop good measurement techniques for understanding it. And so we started by looking at the lowest set of modes in this lattice. So a little bit idiosyncratically, coplanar waveguides, their lowest mode is actually antisymmetric. And so that means that you get something that's more like a P-wave type binding model. And so for the modes near 5 gigahertz, we actually expect this band structure. And so now let's have a look at the data. So here we have a more refined data set. And so the qubit is tuning once through and back again. And so if we look at this data, we clearly see 2 regions, one here and one over here where there are a series of avoided crossings, which ought to correspond to this set of bands and that set of bands. But we also notice that these avoided crossings in these modes are very different in shape. Some of them are bright, some of them are dark, some of them are actually phonoresonances, and this region in here, which ought to be the band gap, is not particularly dark. And so what's going on is that this transmission measurement is sensitive to any way in which microwaves can get from the input to the output, whether that's through the device or around the device. And so there's leakage that's going around, which is interfering with the real signal. And so what we've discovered is that there's a much, much better way to do this measurement, which is to do a nonlinear measurement. And so we do this by repurposing a technique called two-tone spectroscopy that's very, very common in the field. And so the idea is that if you have a nonlinear system coupled to a resonator, you can monitor the resonator frequency, and if you change the state of the nonlinear system, it will shift the frequency of the resonator and cause your transmission to drop. And normally this is used to track qubit modes, but if you're willing to crank your generator power up, you can also track nonlinear resonator modes. And so that's what this data is. We're monitoring at one frequency and driving as hard as we can with a scanning tone. And each one of these dips is indicating the presence of a nonlinear mode that couples to the qubit. And so all of these background signals that are going around the device, they couple weakly. And so now this is a hard band gap. Nothing modes, nothing modes. And this we can compare much better to the expected density of states. The dispersive bands I've shown in a lighter blue, and the delta function flat bands are these dark blue columns, and they're way off scale. And so this is now a nice, pretty nice agreement with what we expected to get. But the set of modes that we were really interested in is the second harmonic modes up at 10 gigahertz. 3 minutes? Okay. I've been talking way too slow. All right, so punchline, these are harder to see, but with the nonlinear spectroscopy, we can verify that this gap flat band is there. And actually, the nonlinear spectroscopy is not the only evidence that we have of our invisible flat band, because we can also track the qubits in the band gap. And so this plot shows 3 sets of data. So the color plot up here is linear microwave transmission. This is nonlinear spectroscopy, showing where do we get these dips. And then these 2 patches here are more conventional two-tone spectroscopy, where we track the qubit excitation itself. And so the bare qubit is making a trajectory like this, but you can see the actual eigenstate turns around long before, because it's bouncing off of this set of flat bands here that we can't actually see in transmission. And so since I have only a few minutes, I want to get to the punchline, which is that we really wanted to use this device to look at photon-mediated qubit-qubit interactions from all of these unconventional bands that we have. And so for that, we need to step away from looking at this resonant regime and move into the band gaps. We go deep into the band gaps, and so now the qubits are exchanging virtual photons instead of real ones, like it's happening here. And so we can get an interaction without inheriting the dissipation of the photons. And so now we're going to look in regions like this. And this is not to scale, but it's just sort of showing you we're looking down here. And this is device actually from this is data from the last month or two. And so this is showing one qubit held fixed and the other qubit ramped through. And so if we're deep into this band gap, we get a very small interaction. And as we come closer, we get more and more of an interaction. And we can also do this up near the full wave modes. So now looking in a region like this, near this gapped flat band and other things. And we can get very similar looking data. This is higher frequency, higher coupling. So we get larger avoided crossings. We also see this interesting little line down the middle here. And so what that actually is a 2-photon transition to the state where both of the qubits are coupled. And so we're very excited that we have made this device, I think really been able to see that our microwave engineering basically worked. And we've really had to develop a whole lot of measurement techniques for this particular kind of device. The standard tricks from single cavity don't work on modified. And many of the previous devices of this kind were with a waveguide rather than with narrow resonator-based modes. And so we've had to do a lot of the development there. I will flash through. We're also looking at characterizing photon-photon interactions in this, but don't have time to talk about that. And so hopefully what I have convinced you is that coplanar waveguide lattice systems allow you to go to new and interesting places of basically sort of spin boson type models, whether you're using the spin to make the photons interact or whether you're using the photons to make the spins interact. We've made this prototype device in one dimension to really develop the experimental techniques, both fabrication and controls and measurement. And so we're very excited with what we can see in this device and already scheming and planning for what are we going to do in 2 dimensions or up in hyperbolic. And I cannot stop without thanking all of the people who actually made this possible, and the funding agencies that supported. So the folks whose names are highlighted in red in particular worked on this lattice project at some stage. And many of these folks were paid in part or in full by RQS to help get us a big enough team to really bring this project home. Thank you. Really? Everything was totally clear? Yes, and so that's the goal of this, is to have something with an interesting tail that that's not just limited to nearest neighbor. For full disclaimer, the flat bands tend to give fairly localized interactions, and so it's work in progress to get really the right lattice and the right drives to get something that a theorist would call a long-range interaction, but it's not a delta function, which is what normally would happen in these systems. So the stuff that's in the band gap, let's see. So the stuff that's in this band gap is big, broad, fuzzy stuff. And so what we think this actually is this device is fairly large, and so there are unwanted modes in the package. And so there are some big dilute microwave modes that allow us to transmit from the input to the output, but couple very poorly to the qubit. And so since the qubit is the source of nonlinearity, if you do a measurement that relies on nonlinearity, only things that actually couple to the qubit will show up. And so if we drive really hard in here, the qubit says, I don't care, do what you want. And the main transmission doesn't change. And so this is really selective to things that are relatively strongly coupled to the qubit, and that rejects most of these very dilute big package modes. It's much more dramatic in this set where the main transmission is significantly uglier, because up at 10 gigahertz there's a lot more crud in the package. That's a technical term. So we wanted to get as much as possible to really fill in these bands, because we're going to get 9 modes per band, and so we would have loved to get more, actually, just to make these bands more continuous. You can really see these individual teeth here. And so the limit there is really set by, we can't let the resonators get too high in frequency, or then we can't measure them. And so Coplanar waveguides are great because you can reconfigure them, and absolutely abysmal for actually how big they are.